university. Subsequently, he kind of worked as a postdoc in various places, including Princeton and Texas A&M with Marlon Scully. I guess Marlon moved to College Station from Princeton.
He had the double position, so
he had double position.
Yeah, so that.
Worked in both, and then also at UC Irvine with Charles Campbell. So then, briefly, he worked as a staff scientist at this, I guess most of you know, the ANSTAR Institute in Singapore. And then finally, where he is currently affiliated his position as a GDM endowed young professor of physics at the State Key Laboratory of Precision Spectroscopy in East China Normal University in Shanghai, where he has been since 2017.
That's right.
For the last 5 years, and he also has this affiliation with Himalayan Institute for Advanced Study in Rishikesh. I guess you're going to say a few words about that, but he has the Dorfman has expertise in a broad range of area: quantum optics, quantum and nonlinear optics, photonics, ultrafast phenomena, quantum thermodynamics, and so on. Rather than taking time away from him, let's listen to what Konstantin had to share with us.
Thank you. Thank you very much for this nice introduction. Can you hear me? All right. Is it better now?
Yeah.
Great. So how much actually time I have? It's about
50 minutes.
Okay. So well, it's a great pleasure to be here in ISC, my third or fourth visit now. But first time certainly in the physics department, and I'm glad that IQTI was able to arrange this visit. So it's an overview talk that I will be presenting today, which is essentially a summary of the research activities in my group for the last few years. These are the four main research directions that I pursue. Today, I guess I will try to focus on these three to please the audience and entertain myself. And in basically the outline, so I, since it's a quantum talk, everything should be about quantum. So I will try to be as much quantum as possible. So the first part of the talk will be related to multidimensional four-wave mixing, and this is one of the spectroscopy techniques.
I think battery might be there.
I think there is no battery.
He's coming with the battery.
All right.
You might carry on.
Can you hear me, or should I increase my sound? All right. So this is the technique which is based on the use of a squeeze light to probe molecular dynamics. Second part will be dedicated to the ultrafast section, particularly high harmonics generation and spectroscopy. And the quantum part here would be related to the squeezing of the harmonics, something new we have recently investigated. And the third related to materials, or how we view materials and our interest in combining this with quantum sensing. So I hope to connect with as many people here as possible. So let me start with motivation. So motivation is very simple, that quantum information and quantum optics is typically dealing with simple systems like qubit, interacting with the complex fields and states of light. And if we want to generalize quantum optics to more complex material systems like molecules or materials, we have to really develop a new understanding of new degrees of freedom, their role in quantum algorithms and quantum optical phenomena. We have to extend them to time domain because the dynamics play a very important role in complex systems. And of course, the new parameters and controls available for this techniques should be developed in order to be successful. So of course, I could not start without mentioning all the inspiring works in the field of quantum nonlinear optics, including the latest Nobel Prize here, and of course Raman as one of the earlier Nobel Prizes. It's of course pleasure to be in ISC. Unfortunately, it's not the old building, which I really like, and the auditorium there is very special. You feel the flavors of the past and the achievements that have been done in the old building. But nevertheless, the field of nonlinear spectroscopy that originate from this nonlinear optics, encompass a lot of electromagnetic wave ranges from radio wave to gamma ray, and various material information can be extracted by looking at the interaction of this light with the material systems. So my talk essentially is a continuation of our early studies summarized in these 3 reviews. The review of modern physics has the formalism. The chemical reviews focuses on non-adiabatic dynamics, or rather the system part. And accounts is an experimental friendly extended version of the formalism to really appeal for experimental realization. So as you all know, the spectroscopy, particularly vibrational, is about the interaction of light and scattering of light from the molecules. We have a elastic Rayleigh and inelastic Raman scatterings, and of course each molecule is a combination of various degrees of freedom, each of which has a signature in the vibrational spectra. So one can identify a fingerprint spectra to be precisely assigned to a molecule, and this is the stationary version of it. This is the ultra-fast version of it, when we use pulses to identify the dynamical features of molecules in order to look at the time domain results. And the ultra-fast spectroscopy is essentially constituted in taking snapshots of the dynamical features. One can use a pump probe scheme in order to probe that. Pump excites the molecular motion, probe probes the motion. One can also think of this type of picture where a potential energy surface representing the molecular structure undergoes excitation by pump, then goes along the potential energy being probed at every time, like this snapshot photo. And the interesting fact is that if we increase number of parameters, for instance, increase number of pulses, we can increase number of parameters three pulses with 2 delays depend on 2 delays, so we have 2 dimensions to explore. But the multidimensional typically refers something that originated in NMR and related to the echo phenomena. When I hide it, it closed the presentation. I just did it before.
Oh, is it?
Yeah.
It's not.
Oh my God.
Sorry.
Sorry.
No worries.
It's gone now.
No, I think
How about now?
this is better.
Yes.
All right. Okay, let's see if it comes again. Last time it came again.
The first time I'm seeing
It's,
Last time it came, it didn't come again. Like, so I had to do it again. So anyway, multidimensional measurement based on echo, particularly in this example, is based on the sequence of short pulses, well separated in time, with the 3 delays. One can record this. One can interact these pulses with the system, then record the signal as a function of the 3 delays, perform a double Fourier transform, and express the final result as a 2-dimensional cartoon. So these 2 frequencies represent these 2 Fourier components, the central T2 time kept as a time. So one can see the evolution of the combination of diagonal and off-diagonal peaks representing various degrees of freedom. It is useful for displaying structural and dynamic information. We separate different information in different dimensions. It's beneficial. We reduce the reliance on the congested spectra. The line shape of these various peaks represent the state of the environment, fluctuations, and things like that. So it's a very useful technique. Now, from the theoretical point of view, if we would like to describe such a system in a simple dipole approximation, we have a dipole Hamiltonian, and any nonlinear response can be viewed as a combination or convolution of the material part and the field part. So the material part is a sequence of various commutators and anti-commutators of the dipole operator taken at different time, and the field part in general is a correlation function of the electric field at different times taken with the state of light, of the input light, which we typically ignore because we're dealing with lasers, and laser is a proxy for the classical light. So if you look carefully at this correlation function, let's say I'm looking at the third order response with the 4 operators, where 2 creations are here and 2 annihilations are here. Indeed, if we take a classical light, it's identical because you know, a classical or coherent state is indeed a proxy for classical in the normally ordered fashion according to Glauber. But if we take, let's say, the entangled photons, this 4-point correlation function will factorize into 2 2-point correlation functions, where creation are grouped together and annihilation operators are grouped together. If we take another state of light, for instance, stochastic, the factorization will be different. So what I'm trying to say here is that the field correlation function is some sort of a detection window to molecular response, and it's a control parameter. Performing the same experiment with different states of light allows us to explore various detection windows. So we may think that the results shall be slightly different by using different states of light. Now, let me take one example, and I will take particularly interesting time-energy entanglement. Why it's time-energy, not polarization? Because I'm interested in spectroscopy, so I would like to explore frequency and time rather than polarization and spin or some other degrees of freedom. So all of us know about the parametric down conversion, where a high-energy photon is decomposed into 2 lower-energy photons, Siegel and Idler. If we take, for instance, type 2 down conversion, where we have a 2 orthogonal polarization in a birefringent crystal, we have 2 important features here. One is the time correlations related to the group velocity dispersion, and another one is the frequency anticorrelations related to the energy conservation. So if we take the individual photon, Siegel or Idler, and look at their uncertainty, it will be always larger than h⁻². But if we take a joint uncertainty for some frequency and difference in time, according to this particular generation scheme, it could be it could yield the EPR-like condition, and that is something which can be used for spectroscopy. So when we can try to design the measurement which rely on this particular uncertainty in order to improve, for instance, spectral or temporal resolution. So natural thing by looking at this to understand that some frequencies, because of the cascade emission and down conversion, can be applied for 2-photon absorption. Well, that's exactly what has been done. And of course, we all are familiar in quantum optics in atomic systems with early work of pioneers. And this is the later realization in molecules, where the 2-photon absorption in a particularly complex molecule is observed. And the first striking thing is the scaling. If 2 photons belong to the same pair, or in other words, they are correlated, then due to the scaling of the entangled state with the input intensity, we can observe a linear scaling of 2-photon absorption at low intensity. Of course, if we go for a higher intensity regime, then these 2 photons may belong to different pairs which are not correlated, so we can recover the classical quadratic scaling. So this was the first observation, which brings, of course, the immediate set of applications and benefits like increased signal strength at low intensity, stable resolution because it's low intensity, and of course new control parameters because the source is different from a traditional laser. So
here you are, the 2-photon absorption is from the entangled photons.
Right.
Is that what is happening? And the
Yes.
entangled photons, how are they generated?
They generated in parametric down conversion.
Parametric down conversion.
Yes. They used to excite this molecule to the biexciton state, for instance, here. And the observation is the cross section, you can say, as a function of input.
The intensity is basically the intensity that is used to generate this, or you are measuring the intensity of the output.
That's right. That's right.
Which intensity is this?
It's the intensity of output as a function of the input intensity. So now, so scaling is one important thing. Yeah.
So is this this is quite interesting? So these are different frequencies, photon, signal and hydrogen.
Yes.
But they are both of them are being absorbed.
Right.
Carrying on this.
Right. But you should ask a different question. You know, usually everyone does it through the virtual state. Why there is an intermediate state here? You want to ask that question? Well, if you don't, it's okay. You know? But I think this is the most striking out of this.
Right,
Yeah.
these are actual states.
Right.
Yeah. So that's why I was asking. Like that's why that question came forward, right? Because usually for two photon absorption, you use the same photon.
Right.
You use a virtual state to carry on this transition, but here you're using a real state.
Right. Right. That's exactly allows you to observe a signal at very low intensity because the cross section is extremely low. Yeah. Exactly.
So this will be quite system dependent.
Correct. And
so
more
you
so,
do this-
and more so on the next slide. So, okay, so the resonant intermediate state is one important feature. Now, you may say, okay, well then signals should be like 1 over detuning square or something like that, very sensitive and so on. Well, let me go to the next slide to show you something even more striking. So this is the simulation we did for a complex system like a photosynthetic reaction center. And this is what we obtain by looking at the populations of biexcitons as a function of the input pump frequency. So this bottom one, we use the entangled pair. And the top one is basically a best case scenario for classical light, where we took two pulses with the opposite chirp, positive and negative, to match the frequency anticorrelations. And you see that the difference is quite striking. So why there is such a big difference? Because I don't know if you're familiar with this big debate between Claude Faber and Marlon Scully about simultaneous excitation of two atoms. And that's exactly the point. One side claims that only the frequency anticorrelations are required. Another side claims that entanglement is important. So, and this is where the notion of molecule versus atom comes. So my answer to this is that molecules are very different from atoms. And of course, if you look at this, and this is two photon absorption, so if we really want to excite a given state, why not use a 2CW lasers and match perfectly the frequency, find the best oscillator strength, and just get it in? Well, this is the answer to that question. So if I look at this blue curve, this is the probability to excite, let's say, this particular state F23 through the two photon absorption. And this is the bandwidth of these two photons. So 0 means a 2CW laser. So you see the probability of this excitation is rather 0. And the reason is, if you look carefully at this picture, and this is what I said, molecules are different from atoms, because molecules have many degrees of freedom. Particularly, it results in various dynamical processes. For instance, this intermediate state can be depleted very fast. So the fact that you use 2CW photons will not help you because of this fast dynamics in the middle. Okay, then the next question will be, okay, we can take perfectly matched pulses in time. Wouldn't that help? Well, it helps to some extent. You know, you can get below 20% efficiency here. And the reason why it's so low is because even though the pulses are matched in time, their bandwidth is so broad that instead of exciting only a given state, you excite the whole band. So that's the limitation of the classical light. So the red line in the contrast gives us almost 90% probability to excite that state under certain conditions. So we need to understand that the entanglement time, which in the type 2 down conversion is, for instance, coming from the group velocity dispersion, is essentially an upper bound for the system to spend in this single excited state. So if this entanglement time is short enough, shorter than the time scale of the dynamical processes, we can view these two entangled photons as a single quantity, which promotes us to a given state. In addition to that, if you generate it from a narrowband pump, then your selectivity in the biexciton band will be also high. So you can excite a given state with this high probability. Again, delta T, delta omega, the resolution in time and frequency for classical light is always bound by this. For entangled light, it's not so, because we can control entanglement time and the pump bandwidth independently, and the result is quite striking. So this brings back the fact that it's a system specific, where we have not only the matching frequencies, but we also have a short entanglement time, and the system should be such that our entanglement time is shorter than the dynamics.
So here's a very narrow bandwidth. Does it mean that the entangled photons have very precise energy, or they can still be?
That's the point. The narrow bandwidth is of the pump pulse, but the individual entangled photons are broad. But when they act together, you can get a narrow band excitation for the sum frequency. Exactly.
But for CW, your bandwidth will be very narrow.
For the entangled case?
No, just for the travel.
Yeah, right. So let's say it's narrow that you can precisely excite any intermediate state. No issue here. The issue is with the dynamics. By the time the second photon wants to promote something to the bi-exciton state, this will be empty, because this is a molecule. This is where the molecule is different from atom. In atom, indeed, you need only frequency anti-correlations. In molecule, you need both.
This gamma factor becomes
Important, yes. And that's why it's a system specific. And some people say the original luck of this early experiment is exactly lies in the fact that the system and the source has been chosen very precisely. Whether it was a luck or a genius, that will time will show. So that's about it for introduction. So now let's go to next step. So basically we played a bit with entangled photons. Now we want to see what else can be done. So the reason why we went further with a squeeze light, because actually the single photon setups are complicated. Working in the molecular system requires knowledge of chemistry. Chemists don't like entangled photons. Physicists don't like large molecules. So it was quite a difficult exercise to perform. But what we done instead, we tried to adapt another setup conventionally used in both nonlinear experiments and in quantum optics, based on the four-way mixing. Four-way mixing, as all of you know, you have pump, Stokes, control, or maybe same pump, and then anti-Stokes. This could be in the collinear, anti-collinear geometry, and this could be in both quantum and classical regime. Means these Stokes and anti-Stokes could be correlated or not correlated at all. That all depends on the particular details of the setup. So the interesting fact for four-way mixing is that the systems and media are quite well studied. It's either alkalized with its gigahertz, splittings, which could be adapted for the Brillouin sensor, or it is the solid-state systems like vacancies, color vacancies, and diamond, which have a nice narrow band because it's a low temperature, and also large splitting of the hundreds of gigahertz, which could be adapted for Raman sensing. So this is the earlier, recent demonstration of the Brillouin advantage performed with squeeze light done by Girish Agarwal's group in Texas A&M, where they show suppressed background and high signal to noise ratio using the squeeze light. And there was an attempt to do the same thing with Raman, adapting certain type of quantum optical interferometers to benefit from this. From our side, we went to essentially a microscopic detail of this, because if we want to use the same setup that quantum optics experiment used, but transform it into spectroscopy, we need to add a possibility to scan frequencies and go through particular resonances. So as you know, in the squeeze light generation, this transformation gives us essentially a photon number of the probe and conjugate, or Stokes and anti-Stokes, related to the four-way mixing gain and input photons. This is a seeded process, so you have a strong pump and weak probe mixed on the sample, and the conjugate or anti-Stokes beam is generated spontaneously, and then we can essentially detect either intensity of individual beam. We call it classical measurement because it's just a photon number, or we can detect the so-called noise figure, which is a high-order correlation, or it's a balanced homodyne subtraction measurement. You take intensity of Stokes, anti-Stokes, subtract them, measure the noise spectrum. So this we call quantum. because it reveals the correlations between the two quantum beams. And the interesting part here is that it's related to this four-way mixing gain, which is typically a number. It is number for a reason, because all the processes typically are off-resonant. But if we want to use it for sensing or spectroscopy, we have to be able to scan the frequencies and go through these various resonances to reveal the chi3 of the process. So we went through the great work of detail, doing all these QET calculations to address all the details of this chi3. The interesting fact, this is just one of the components, is that we have this two photon resonances in the middle. One of the Green's function gives us that, which is Raman or Brillouin. So this is the essence of this four-way mixing in quantum regime. We would like to address Raman or Brillouin, and this is exactly where it comes from, if we look at the calculation. And I will not bore you with the technical details here. Basically, we use essentially a super operator. You have a super operator, super professor here, who contributed to this development, quite some time ago. You see his name is here. And we basically address the point that the classical field, the response function, is different from a quantum field response function. Remember the point I made about the detection window? That was one point. So you have scaling, you have detection window, and this is probably the most fundamentally important. Maybe not so much for application, but for fundamental research, this is the most important part. The quantity itself, which we call chi3, is different for quantum light and classical. Let me try to explain it in a very brief example. So the effect of back reaction, for instance. So the state of the field is modified while interacting with a sample. So sample modifies the state of the field. It means that the standard sequence of field matter interactions in the nonlinear process, which we conventionally called chi3, is just one of the particular sequence related to the nature of the field. If the field is quantum, back reaction will make sure that this quantity is different. These plus minuses represent the commutator and anti-commutator nature of the field. For classical field, the commutator, or E minus, is 0. That's why the particular combination, which we call chi3, is given in this form. Whereas in the quantum case, it's not the case. The field has a commutator, which is non-zero, and the quantity, which we call chi3, is different. Let me just...
Sorry, that would be true for any higher order.
But it's the same order.
Right.
They both are chi3, means it's a fourth order nonlinear process. But the sequence of interactions and the way they combine into this so-called tensor are different. Just to give illustration, this is parametric down conversion. The left column represents a semi-classical chi2 in this case, and the right column represents the quantum version of the chi2. You see that even though it looks in a way similar, but actually it looks quite different. The position of resonances is the same, but the amplitudes are different. It's even more striking for chi3. So the red curve is the semi-classical, the blue one is the quantum. So you see how different it is for the same parameter, for the same order and linearity, for the same position of resonances, but you see somewhere you get imaginary part, somewhere you get the real part. This goes together and you get a completely different response function. So I hope this is something that you can carry on from this talk, that the susceptibility, the nonlinear process occurs in a different way, whether we use classical or quantum states of light. It's a very fundamental thing, in addition to more maybe fancy and applied thing like a scaling and detection window, which is easier to understand. Yeah.
Sorry. So what kind of different
Different information here means, it's a very simple model system, right? So that's why the spectra looks slightly different in some way. But think of this as a degrees of freedom. Some of them will not be visible, some of them will be visible, just because you have a very different response function, right? So you will be learning a different information about some particular degree of freedom by just looking at the spectrum. So interpretation, remember we discussed this morning, spectroscopy is all about interpretation. So you want to learn something about the system?
No, so let me rephrase the question. So when we look at chi3, So chi3, there are peaks in chi3 where you are hitting physical resonances in the system, whether you're creating some
Right.
excitations, you have large chi3. So for the, and that's all classical, like semi-classical.
Yeah.
So in this case, when we're using quantum light, we're hitting the same resonances.
They'll be either same or like here, for instance, you see it's a real and imaginary part. So you will highlight a different kind of, the resonance is the same. Position of the resonance is the same. But your, the information that you learn is quite different, even by amplitude. Right? So let's say you look at the vicinity of this resonance. This is what you learn classically, and this is what you learn with a quantum light.
So okay, so apart from amplitude of chi3,
Yeah.
that's what I'm getting. Trying to understand what other. So
Well, chi3 has only amplitude and phase. So in this case, it's real and imaginary part. Both of them are affected by the choice of the quantum state.
Okay, so it's not the other, some other resonances which are not visible with classical light.
It's not the, okay, let's say you have a complex system where you have a lot of resonances. So some of them are just not visible. They're below your resolution, right? And you use a different state of light, and all of a sudden you have a giant peak at the place where there were no peak before. You know that it should be there. It's just you can't see it. You look at your conceptual structural model, and okay, there should be a resonance here. Maybe it's weak. Maybe oscillator strength is small or something like that.
It's more sensitivity, but not like pulling out some forbidden transmission. That's not what it is.
It's not it's more sensitive. It's not like it's larger. Here, for instance, you see imaginary part for classical is larger. It's just different. It's different. You know. So that's that's what it is. If you want to think of the application, let's say you have some nonlinear device that works on this particular frequency because of the giant nonlinearity. Maybe that giant nonlinearity works only for the coherent laser source. If you use another source, it will not work as nonlinear, and you will think, what is the problem? Is your source not strong enough? So it's not just about strength; it's about the quantum nature. So you will have another nonlinearity on a different frequency. But again, structure is the same. You see, they all are related. All the resonant positions are same because the structure is the same. So in the case of simulations that we did, so maybe I will, because of the lack of time, I will move directly to the experimental part. So here, basically, I'm just demonstrating the silicon vacancy simulations that we did, and look at the new information. It's all fancy, but probably this is more important. So this is what we did in collaboration with the experimental group. This is the 4-wave mixing in a rubidium vapor, where it's just a single wave mixing. We have a cavity here. You have strong pump and a weak probe, and conjugate spontaneously generated from this wave mixing. And there are two detectors here. So one can either measure the gain of the probe, right, through the transmission, or one can measure the noise figure, which I mentioned before. So we call this classical, this is quantum. So just by looking at the comparison of these two, you can see that this has clear, let's say, 4 resonances. This has 8. This looks better resolved, right? And of course, you can ask that maybe this because I use the log scaling. And the result is if you take log scaling of this, you will still see 4 resonances. They will be just better resolved. But just in like Agarwal's work, where they suppressed the background, and that was the reason for higher signal to noise, here happens exactly the same thing. We have a highly suppressed background, which is associated with the fact that we have essentially a hyperfine structure with the AC shift and splitting. So we have a bunch of transitions here. These are dressed, AC dressed resonances. We can identify each and every resonance that is basically detected as a combination of these various components in the susceptibility tensor. And of course, we call it chi tilde because it's not really chi 3, because each of these resonances is dressed by the strong pump, because in the experiment, pump was quite strong. And this is how we can compare ourselves with a theory and experiment. This is the classical probe gain. so we can very well explain each and every resonance here. And this is the quantum case. This is the simulations, so they look pretty similar to the original experimental data. So we can learn it basically about, I mean, it's a rubidium, so it's not that fancy, but you know, it's a very clean system. So we were able to identify all these AC Stark shifts and things like this. Another very important point here is that this measurement has been very robust to the noise. We asked our experimental colleagues to add a random noise to the probe. And basically, if you try to measure anything with a random noise, which fluctuates in time, this is time, you see that the classical transmission is also fluctuating as expected from the simple, you know, consideration, because you modulate something here too. And at the same time, this red line represents the noise figure, which is quite stable because the noise is correlated. So this noise is basically something that we have to take into account when we look at the correlations. And the quantum measurement, the balance, homodiene subtraction measurement, is robust against this noise in both classical and quantum regimes. When I say quantum and classical, that represents the boundary where we have squeezing, this dark part, and where we have no squeezing, which is this light part. These are two examples. So in summary here, extension of quantum techniques to include another states of light, like squeeze light, and use conventional wave mixing schemes. It's very fruitful. We are able to extract information from the measurements and understand it from theoretical models. We also have effects like of cascading and other kind of interferometric setups that we can work with, like SU11, for instance, to improve further the squeezing and resolution. And this experiment basically shows that indeed there is a lot of potential to essentially transform the typical quantum optical experiments for the quantum light generation into the quantum spectroscopy using exactly the same setup. So in the second part, I will start with a quite different setup, related to the high harmonics. It's a physics department, so strong fields is beautiful. We have a lot of ways to generate essentially a broadband light in the high harmonic regime. There are a lot of applications of the high harmonics, from the electronic coherence measurements to resolving molecular dynamics, orientation, and so on. So the question is, there's a conventional models, a three-step model, strong field approximation to describe these processes. What is there to do in the end of the day? Well, we are very inspired by Raman. So we took our early work and stimulated Raman in X-ray, where we basically excite the core electronic states to probe the valence electronic states dynamics and try to find connection with a three-step model. This way, we develop so-called strong field stimulated Raman scattering, which is essentially a dressed way of combining two valence electronic state via some nonlinear strong field process, particularly ionization, free propagation in electric field, and recombination. The result is the same. We couple coherently two valence states, but of course the physics is very different. Now, if this is the strong field Raman, and it is Raman in a way that this is an inelastic scattering across the valence states, is there a way we can describe it also like Raman, rather than relying on a complex strong field approximation? And actually, we attempt to do that. We developed an extended diagram from QED to include strong field effects. So what we did actually is we kept the valence state contribution to be perturbative while keeping the free electron contributions non-perturbative exact, putting the action into place using the strong field approximation. Why this works? Because strong field approximation neglects excited state because they are so small. What we did is just say that excited states can be included, but can be included perturbatively, whereas the free electron degrees of freedom are treated non-perturbatively. So this way, these wiggly diagrams, essentially a generalization of the diagrams on strong field. Yeah.
Here you're using this electron as a exciting, so you're analyzing the.
Yes.
And then this electron is
recombining back. Yes.
back.
Yes. In the middle of that two processes, he gains a lot of energy from the electric field. It's a free electron motion in electric field. So that part is non-perturbative.
Yeah.
while the two bound state transition processes are treated perturbatively.
So in a sense, you're proving some ionized.
Oh no, we don't probe ionized. Ionization is here just to facilitate this transition. In the end of the day, we just define an effective coupling between the valence states, which has a field-dependent Green's function.
These two things are completely different, right? Because in one case you're ionizing, and then your kind of P2 process is through the electron.
Well, P1, P2 is two pulses, but this down arrow is the. I mean, these are two different. It's like a pump probe.
Yeah, I'm looking at the first figure and the second figure. P1, P2.
Yeah, this one.
Is something like first arrow, thick arrow. Then the first figure.
This one.
P1 is.
Oh yeah, sure. This is the X-ray. This is just analogy, right? This is the X-ray laser which drives a core transition. Now, no ionization, just a bound state, but these are core states, deep shells, right?
P1, P2 prepare the state.
Yes.
And maybe this arrow prepares the state.
That's right.
Right.
And the second one probes it, and the second one probes it the same. Yeah. So basically, if we can essentially define as effective coupling or polarizability for this strong field Raman process, we can then use a perturbation theory and use all the beautiful nonlinear optics which we typically do in a weak field. Let me skip the details here. This is essentially a comparison. So of course we don't use a very high intensity, and this is the lowest order perturbation theory. So if I need to be more in agreement with a high intensity, I have to add a few more orders. But this is basically 10 to 12, 10 to 13. And you see the agreement between exact solution of time-dependent Schrödinger equation, non-perturbative in any way, and our diagrammatic contribution is quite in a good agreement. And then with a higher intensity, we start see some deviation and so on. Of course, it is well known if we would just keep perfect perturbation theory, we would never get harmonics. It will be just one harmonic, because that's the nature of the linear response. But here it is very clear that this so-called semi-perturbative model works well while we save a lot of computation time. It's something like 36 hours versus less than 10 minutes if we look for lowest order signals. So, and in addition, our scaling is always in the harmonic regime. So formulas are easy because we can read them from diagrams. Once we define the action, we just read them from the diagrams. We can generalize it for multi-pulses, which I show next, and we can apply it for large molecules. That's the most important thing, because typically strong field physics is always working with the small molecules because they require molecular alignment. Big molecules cannot be aligned, so they are not even considered. And we have other ways to eliminate inhomogeneous broadening, so alignment is not needed. So this is how we have various harmonic signals. If we take the Fourier transforms, we can get a very nice electronic coherences across multiple electronic volts. And you see that different response order of this kind of semi-perturbative response gives us a different peaks. Their amplitudes are different, so we can, it's a very simple model, of course, but we can really learn about electronic coherences by looking at different perturbation orders. And to make another step forward, we basically look at the wave mixing in this high harmonic regime, looking at how strong fields are interfering. So we have essentially a combination of harmonics originated from two pulses here with a phase matching. We look at a proper realistic model for a molecule. We use this so-called wavelet transformation to keep track of the phases. And this is how we got the phase matching. So basically, this is harmonic order, and this is the detection angle. So we see that for a specific pulse duration, we have a very well-defined phase matching and combination of these two numbers. So each two numbers represent the harmonic of the pump combined with the harmonic of the probe. So we can select particular range, particular phase matching, and particular combination of harmonics in order to analyze the spectra. And not only that, we can also see which of these ranges of spectra lie in the vicinity of some multiphoton resonance. For instance, in the large congested spectra, we can identify only sections of the spectra corresponding to particular case of multiphoton resonance. So, for instance, 3-1, 4-1, and 5-1 means third harmonic of the pump combined with the first harmonic of the probe. fourth of the pump, first of the probe, fifth of the pump, first of the probe, gives us a very different picture. So we can really look at the structure to identify why these resonances are so different. So essentially, this is the phase matching selection together with the pulse optimization. And of course, as I promised, everything should be quantum. Harmonics can be also quantum, and recently it became a very interesting direction people pursue, looking at the deviations of the coherent state statistics of the high harmonics. Things like Schrödinger cat is a natural thing. But we looked again back to what we did with the four-wave mixing and thought, why don't we propose something which involves a similar wave mixing but in the high harmonic regime? So let's say that we have a IR pulse. We split it into two halves. First, it's a strong IR pulse, so it can generate high harmonic probe, and that probe uses seed for wave mixing in the second wave mixing process, combined with a pump to generate harmonics. So if we look at the energy diagram, it's a pump, Stokes, pump, anti-Stokes, but everything occurs through this continuum state, ionization, recombination, and so on. So basically, it's a strong field analog of the four-wave mixing, except that these are not four waves, it's multi-harmonic fields, and they mix in this strong field regime. So we can use our formalism to extend it to this domain. And the interesting fact is, indeed, if we look at the statistics, Wigner function, noise figure, gain, we can see essentially quantum features here and the proper squeezing in the Wigner function due to this high gain. Apparently, if you take a really weak harmonic and use it as a seed for another wave mixing, you can really amplify it by a lot. And this is something that we are, discuss with our colleagues who do experiment, and they say that it's quite possible. Basically, it's at the path of stimulated emission. You know that high harmonics are not yet in the form of a laser because of the cavity issues and stuff. But if we find a way to do the stimulated emission and use quantum features like squeezing to control the statistics, we are on the path of maybe first coherent stimulated high harmonic laser type of device. So
what is the requirement for this as far as experiment? This is your simulation.
Yes, yes.
What will be required? High harmonics?
Well, there are too many. It's a both requirement. The most important one is that it's a pulse duration, of course. It's a wavelength, and your system, everything together should be in a very specific phase matching condition. Actually, this is unpublished work, so I really cannot show you the full set of simulations with that. So all I can tell is that the pulse duration, the system itself, the ionization potential for various states, everything should be sort of in a favorable domain.
I mean, you mentioned that high harmonic generation itself is not an issue. That is something that
it's not an issue because
that's not an issue. In this case, where you're actually able to effectively generate this sort of squeezing, using the
way
harmonic mode,
right.
So that's what I'm trying to understand. That what would be the requirement? You said the temporal duration would be.
Yes. Also, it's important the phase matching. Okay, because you have to phase match a harmonic field with another harmonic field. That's a very tricky thing.
So, is a system dependent? You mean the system on which this is going to?
Yes.
You're talking about.
Right. It's a system, the medium of wave mixing.
But also, there is also the parameters you have to control even for the generation process.
That's right. Because it relies on two cascaded for high harmonic generation. First, to create a seed. Second, to match it with another, to stimulate essentially another high harmonics. So.
And the cat step that you mentioned, that has been demonstrated.
Yeah.
It's a
Yes. No, it has been demonstrated.
On what? Atomic system. So
yeah, it is atomic system.
not like a molecular or something.
No. So in summary of this part, essentially, we have a lot of applications of the strong fields, which we just start exploring the quantum nature of this, because we first had to develop the formalism which is capable of describing this complex light-matter interaction regime. But I think we're in the right path, and XUV is a very exciting field, and quantum optics in that range has never been more possible than it is right now, especially in this, if we are able to control these high harmonic fields. But again, we talk a lot with experimentalists. Currently, there is a wave mixing experiment in progress. Let's see. I don't want to, promise something and then it's just not working. So in the last 5 minutes, I just want to quickly go, or rather run through the last section of the talk related to the metasurfaces. So essentially, metasurface is a modern replacement or attempt to replace a diffraction optics with a sub-wavelength resonators on the surface of the material. The fact that you have a sub-wavelength manipulation of the light wavefront allows to, for instance, experience modified Snell's law, where the phase gradient created in this way allows to experience anomalous refraction, reflection, and diffraction. So not to bore you into details too much, the important role which is played in this type of metasurfaces is the Pancharatnam-Berry phase. Pancharatnam, again, being in the place of Raman, it's a big deal. And I just learned recently that Pancharatnam was a relative of both Raman and both Chandrasekhars. That's a very interesting news for me. So Pancharatnam-Berry phase is related to the rotation angle, essentially, on the surface of the substrate, which can be grown and controlled in sub-wavelength regime. And then these metasurfaces can be applied for many interesting things, including quantum optics and spectroscopy. So we went to a great deal of detail to develop the simplest possible theory based on mesoscopic electrodynamics, where we essentially describe the unit cell on this metasurface with the simplest geometry. And this is the PB phase. We have a uniform rotation of the antennas inside the unit cell. We can define, essential polarization for it. Again, first we started with a linear regime. We can look at the transmission field, propagation of the field, identify the co and cross polarization degrees of freedom here. And our mesoscopic simple theory gives a very well-defined answer why we can really observe only first lowest diffraction orders in the scattering rather than looking at all possible orders, because we have oblique incidence, we have a propagation wave condition and imaginary momentum if we are violating certain phase matching conditions. And from the experimental point of view, our collaboration allowed us to basically grow a structure to demonstrate the effect. So our goal was essentially to reveal this Pancharatnam-Berry phase in direct measurement. Most of the measurement we have seen before always talk about this indirectly. We wanted a direct measurement. So essentially what we did, we took a Mach-Zehnder interferometer, and instead of beam splitter, we put this metasurface and we scan it across the interferometer in order to experience various jumps in the phase. And essentially this saw-like structure demonstrates the Pancharatnam-Berry phase in a discrete way, basically. Each element, when it's scanned, capture just a specific phase, and that's exactly the measurement that has been shown. It's quite simple experiment, but the tricky part was to create the structure with a perfect 50-50 beam splitter-like features. We went.
So what is the advantage over a normal beam splitter?
Yeah, I mean, it's a Mach-Zehnder. So right in the beginning of Mach-Zehnder, you have a beam splitter. So we just replace it by metasurface.
Yeah, I know. But what is the advantage of replacing that?
Oh no, we just use it to measure the Berry phase in this structure. So that was the idea, just to test whether we understand it, whether it's exactly what it is, and it was. So it's a linear regime. Now we want to use this PB phase in order to look at the nonlinear response. So we took our theory, generalized it for nonlinear case. Specifically, we have a polarization sensitive excitone states here, and we have multiple, tensor components. So the interesting part is here that we can design a sequence of wave mixing fields, which are polarization sensitive, to extract any given polarization component. This is chi3 actually, And the interesting part is because we have full control over the frequencies, we can also experience both stationary and transient charge densities. So if we want to learn about the structure itself, eventually we would like to put some molecules on it and look at the near field enhancement of certain type of resonances. But this is just a bare structure, just to understand it better. So we can basically assign and identify each individual resonance to a specific plasmonic mode in the system. And finally, the quantum. Again, it's a shortcut, unpublished work, so I have to basically present essentially a result. So what we asked ourselves is there any way we can do something with the no-go theorem? So no-go theorem for Bell analyzer is that if we take a standard Innsbruck scheme and we use only linear component like beam splitter and polarizing beam splitter, we can only distinguish 2 out of 4 Bell states. So we thought, okay, if we use metasurface, can we get something better than that? So this is the result. We took the, we replaced the polarizing beam splitters by a special type of metasurface. It's a multi-pixel metasurface. And this metasurface combination allowed us, and we have a full simulation. Again, I just showed the basic thing. Basically, we can control, asymmetrically the phases of EX and EY after transmission through the metasurface. It means that if we really look at the, so this is the effective quantum state that comes after this transformation by metasurface. This is the state we detect. We can identify all 4 Bell states in the essentially, well, it's not a single measurement, so I'm not going to lie. It's 2 measurements. One measurement for arbitrary polarization input gives us 3 out of 4, and second one gives us the remaining 4th. So again, work is in progress. We really hope that we can do, we can have a single measurement which gives us all 4 Bell state, but at this time we couldn't do that. But the important part is that it's the first time that we were able to demonstrate that for arbitrary polarization input, arbitrary, it's not a projection measurement that we just select a given Bell state. It's an arbitrary input. We can identify all 4 Bell state at least in 2 measurements. So I'll finish on the summary here to say that metasurface is also a very interesting material science problem, and we have a lot of quantum optical features and projects that we're undergoing. This is essentially something that I could only briefly touch, unfortunately, but we can discuss that in more detail if you like. So just to acknowledge, if you have any interest in submitting your journal to the science, ultrafast science journal, you can mention me as editorial board. I can see what I can do. But it's a nice journal, it's a science partner. So I want to acknowledge my group. So research professor, postdocs, PhD students, master students, the funding, collaborators. And as I promised, just to mention briefly, the Himalayan Institute of Advanced Study in Rishikesh, it's a registered Section 8 non-government organization in the state of Uttarakhand. We have an upcoming website. Essentially, it's basically a research center for people who are in between. You have a master student who is waiting for his PhD to start, has a 6 months, or you have a PhD who is waiting for a postdoctoral contract to start and has a few months. We can host them for free. They can come, stay with us in Rishikesh, do the project together. Or if you have a lot of applications from students you can support for a short project, we can collaborate, identify a project. The student stays in Rishikesh, we do project together, and everyone benefits from this experience. As the result, we publish some nice work, and students will be happy. It will help them to apply for a better graduate school. So we have a building under construction. It's near Ames, Rishikesh. If you're familiar with the place, we have a local support of the MP, a partner organization in Dehradun, which is another NGO institute. We have a nice trajectory of our students who are basically stopping by, doing some good projects, and then going into even better places. So For those of you who are interested, please email me any of these emails. So with that, I would like to thank you for your attention and thank you for your time.
Thank you, Konstantin, for the very nice presentation.
I have just one point. One is that when we talk about integral light, there's a for this time correlation. This is given by how do you control this? Is it controllable smoothly or?
Right. So what I showed there was our early work, I think 2013, and essentially thickness of the crystal is directly proportional to the entanglement time. Entanglement time is a thickness of the crystal divided by the group velocity for a given polarization, and their difference gives us the entanglement time. So back then we just said, okay, perform experiment with a bunch of crystals of different thickness. Shortly after, the SLM has been developed for single photons. So instead of relying on entanglement time from the generation of the crystal, we can use the pulse shaper to just shape the entangled photon pair. So Michael Reimer in Oregon, they have all the technology for that, and yeah, it's pretty good. Yeah, you can control it essentially just like you control a pulse shape of with a special light modulator.
About the last work you showed, where you could measure the 4 Bell states. So are you saying that you come up with any arbitrary beams, and it will tell you what the combination of the Bell states you need to generate this arbitrary beam?
Well, the beams have arbitrary polarizations, right? They are, let's say you send some superposition of vertical and horizontal, and the final measurement will just tell you this coincidence between these two detectors gives you psi1. This gives the other combination gives you psi2, and the other combination gives you psi3 for a given basis, of course. But this basis is the same. It's not like we're rotating the basis and getting like this is a shortcut, you know. So if basically if we really believe the no-go theorem, and we really believe metasurface is a linear device, which for the most of the things I showed it is linear, then this is sort of a violation of the theorem.
Only the combination of polarization that splitting into
Yes.
the Bell states. It's not like I can come up with any arbitrary light, for example, thermal light or any arbitrary state.
Yeah, sure.
And it will tell you.
No.
What combination.
No.
Okay.
That will be nonlinear, right?
Yes.
There's a question from online audience.
Yes.
Please unmute yourself and ask. Mr. Vivek, can you hear us?
Vivek, you can go ahead.
Yeah.
You can hear us.
Yeah. Can you hear me?
Yeah, we can hear you.
Yeah. Hi, Konstantin. Vivek here. So actually, I wanted to ask about when you were showing the like 2 questions from first part of the talk. One was when you were showing with entangled photons how chi3 changes. So there, my question was, is it correct to say that chi3 changes, or is it simply because the line shapes change simply because there are more interference pathways that become available because the causality is violated within the time frequency or a time energy uncertainty window of the entangled photons?
Yes, you're asking if the causality violation causes this change in the line shape and intensity for the chi's. Yes. So what I said, the Beck reaction is one of the example, but overall it is a causality which.
Sure.
Okay. That's exactly.
And then and then I guess the other question was so this is again about the entangled time parameter that you mentioned. So let us say that I was interested in measuring the anti-diagonal line width, or the which tells me about the 1 quantum decoherence timescale using multidimensional spectroscopy. So in that case, let us say that line width was very small, meaning the 0-1 decoherence time scale was long. So in that case, if it's longer than the delta t over which the photons can remain entangled, can I, so that measurement would not be possible, right? Am I understanding it correctly?
Again, you're asking if the measurement of multidimensional spectroscopy for slow 0-1 decoherence will be impossible, because why would it be impossible? Because our entanglement time is too short?
Yes, yeah, that's what I'm wondering.
Yes, so in multidimensional spectroscopy, we have a work back in 2014, again, in response to the paper by Marcus and Reimer about this delay scanning protocols, where we identify the limits for the scanning capacity, right? So you need to make sure that, yeah, I mean, instead of entanglement time, you have this shape, pulse shaping, right? So you have to scan in a certain way the two photons, but that time is not related to 0-1, actually. That time would be related to some population, as far as I can remember. So for 0-1, you can shape as much as you want, because those would be represented by amplitudes of the same photon. The entanglement time is between the two entangled photons.
Okay.
So that time scanning would be the T2 rather than T3. Yeah.
Okay, I think I understand what you're saying. I'll probably have to look at the paper again.
Right, but the specifics would be, of course, appreciated if we can, we better discuss. So otherwise, maybe I misunderstood the detail of your question.
Yeah, I think probably it requires a longer discussion. So, all right, thank you.
Thank you.
Any other questions? If not, thanks, Konstantin, for a very nice presentation. And
thank you very much.
But also thanks to all of you for staying here and listening to him patiently. And before we end this, you want to. So this is the Memento map of the IQTI. So very happy to present this.
Thank you. It's a secret, that's why it's in the bag.
No. It's an open bag. Sure. The audience probably doesn't know. If you want, you can share it.
My share, you don't need to do it.
Wow.